Hello viewers of mine, this is a What the Physics video. This one is on centripetal and tangential. Ooh, I wonder what those mean. Ooh, how exciting. But, before we get into that, we've got to summarize what we just learned about. Hello, we've got to talk about what is circular motion and different types of speed, compare, contrast, do all that good stuff. So, things that we could be writing into our notes right now. First of all, what is circular motion? That's as we go around in a circle, but it doesn't have to be a full, complete circle. It can just be part of a circle. And there are various reasons that we'd be going into the circle and going around in a circle. And we're actually going to discuss the forces involved in that. But listing out some examples of circular motion would probably be a good idea. And then when we get into speeds, now we can talk about translational. That's when you're going from one point to another. That's translational. So even writing that down maybe would be a good thing to do. So for translational, that is when we're going from point A to point B. So from point A to point B. The point is you are actually moving from one location to another. Typically that was straight line motion, although technically, even though we often called it linear, it could be going around in a curve. And then tangential is when we're talking about from point A to point A is what I was referring to it as. You say, what, how are we, what, huh? Remember that was when we were going around in a curve or in a circular path, and we're talking about some specific spot on here going around like that. That is as opposed to this spot right here going around like that, or the spot like right here going around like that, or if we made it even a larger radius. Anyhow, these are both going to be distance traveled divided by the time, and that means we're going to be using meters per second. I'll put brackets around there for the units, meters per second. Then we have angular velocity, which is related to tangential because we're talking about going around in a circle. But in that case, we're talking about how the entire object is rotating. Okay, so this is going to be rotational motion. And we're talking about how much, or like what percentage, you can almost think of it as, of the rotation have we gone through. We're normally going to just say like rotations, rots per second. Okay, so units are going to be different. It's not distance over time, it's angle per time. So you can do rotations per second. You can also, when you go into AP Physics C, you will learn more about, well, I guess you could use radians per second there. Very closely related to rotations per second, but just a little bit different. Okay, but we're talking about, in this case, the entire chunk of this object. Oh, goodness. This whole thing is going around in a particular speed, and it doesn't really matter what the radius is. The angular or rotational velocity doesn't care about how far you are from the center, from the axis of rotation. We don't care about the radius. Okay. Other things you can put in there, go ahead and do a little compare contrast. You could also talk about period and frequency, just making sure we understand about that. But yeah, it's always, and then doing maybe some examples like, oh, are we talking about increasing the rotational speed? Are we talking about changing up the tangential speed? How do we do that? How are they related? And so on. Okay, good. All right, now let's go ahead and go into the learning targets. Oh, love learning targets. I can demonstrate how an object moving at a constant speed can accelerate. I can? Oh, yes. Oh, yes. And I can apply the appropriate equations for the given scenarios. Equations are good. We have a whole new set of equations here. It's going to be awesome. And then I can identify the forces that cause the circular motion and predict what would happen if the forces or other components are changed or removed. So here we have accelerating with a constant speed. Back when we learned about vectors, we had distinguished between speed and velocity. So remember, velocity is how fast we're going in a particular direction. Speed is just how fast we're going. Okay, and that distinction here is going to be important because that is how we are accelerating. Acceleration means we have a change in velocity. It's not necessarily a change in speed. You say, well, okay, what is that? It means we have to be changing one or both of those components of velocity in order to accelerate. If our speed is constant, then that means our direction must be changing. So imagine this car is going around the curve. Right here, this car is going like up the page, if you want to treat that as north, okay? And then the car is going north and west, and then we have just plain west, and then in a moment later, the car would be going southwest, and so on. So even if the car's speed is nice and constant, if we put it in cruise control, going around this turn, cruise control doesn't lock in the steering wheel. We're still able to change our velocity by changing the direction. If we have a change in velocity, then that means we are accelerating. Okay, sure. If we're accelerating, then that means we must have a net force. That goes back to Newton's first law. Oh yeah. Objects in motion, stay in motion, objects at rest, stay at rest. Unless there's a net outside force, I got it. And then you can also do some derivation stuff. I'm not really going to go into that, but this is kind of the start of derivations, how you would figure out what the equation is. I'm just going to tell you, hey, this is what the equations are. Okay? We do have to deal with new equations here. Now, I say that speed is still going to be pretty straightforward. That's distance over time. You say, okay, fine. And if we're talking about going around in a circle, then we know the distance around a circle is going to be the circumference. And we know that the circumference is 2 pi r. Okay, so if we have a circle, then we know that going from here, oops, come on, start marking. Okay, so we are going to go around here, all the way around here. If you're marking properly, you silly goose. Okay, so that is going to be the circumference, and we already defined what the period is. The period is just the amount of time it takes to go around in a circle. So if we divide the circumference divided by the period, that is going to be the tangential speed. Now we're going to simplify and we're going to call it v sub t. You say, wait, doesn't v stand for velocity? Yeah, but we're still going to call it that. Tangential velocity, because we're really just focusing on, or we're recognizing that we're changing direction, okay? So because we recognize we're changing direction, we're going to just kind of use speed and velocity a little bit interchangeably. Just go along with it. So because the acceleration and the force are for curving motion, we have special names for them. So we have these equations, and we have special names to go with these special types of acceleration and force. So first one is the centripetal acceleration. And you say, oh yeah, acceleration. Don't we get to use the big 5 equations? No, actually we don't. Those were only for a constant acceleration. If you remember, we talked about that back then. You say, oh, yeah. So it's not just changing acceleration as in you start needing derivatives because the acceleration is changing over time. Numerically, I mean changing direction is going to be causing us to change time. So if we have our car going along right here, this is the velocity of the car, then the acceleration of the car is going to be inwards like this. If we have the car right here, the velocity of the car, this was supposed to be referencing the image from before, the acceleration is inwards like this. So the direction of the acceleration is changing, just like the velocity's direction is changing, which means we need to have a new equation. You say, well, where did this equation come from? Well, that's what I was saying about it's a bit complicated to derive, but it's easy enough to remember. Centripetal acceleration, AC is equal to v squared over r. Okay, now what is this? What is this guy here? Well, if I take the idea that velocity is equal to 2 pi r divided by t, and I go ahead and plug into here, I'm going to get A sub c is equal to, as we mentioned, v squared over r. Lovely, lovely, lovely. And now I can substitute in, I have, let's see, 2 pi r over t. That whole dealy-do is squared, and divide that by the r. Now you say, whoa, that's crazy. That's really complicated. It's not so bad because I'll go ahead and distribute the square. 2 squared is 4, then we have pi squared, and then r squared over t squared, and then all over r. You say, okay, how's that any better? Well, this r cancels out with the square here, and that's how we end up with this guy here. So it's easy enough to derive. Now you say, why would you want both equations? It just kind of depends on what you're given, what you have, what you're looking for, that type of thing. So if we are given velocity and radius and we want to find acceleration, then use v squared over r. If you are given the radius and the period and you want to solve for acceleration, then you'd use the second one. Then we have centripetal force is equal to mass times centripetal acceleration, so F equals ma. So it's really just mass times this times this. So that's not a big one. So really the only new equation, officially totally new equation, is this guy. Everything else is kind of just derived from it. Okay, now we will be using uniform circular motion here. That just means we're going to keep it nice and easy. So for uniform circular motion, centripetal force and centripetal acceleration are always going to be parallel. We'll learn more about centripetal force in just a moment. And they will always be perpendicular to the tangential velocity, as I was drawing here. This guy is the velocity, and then this guy here is the acceleration, centripetal acceleration. Also the direction of the centripetal force. All right, so let's talk about centripetal force. Centripetal force, F sub c, is the net force towards the center of a circle that causes uniform circular motion. You say, oh, okay. The unit for centripetal force is newtons because force, right? Now, the centripetal force is not a new force. It's not its own force. It's just another way of saying the net force. Remember when we were talking in the force unit, when we were talking about, this force on the y plus this force on the y minus this force on the y and so on. And that was the net force on the y. And you do the same thing for the x, right? Well, how are you going to do that if your force keeps on changing direction? So what we're going to do instead is we're actually going to use a different coordinate system. Technically it's polar coordinates, but don't worry about that because I know that might scare people. But it actually works out quite nicely here. So we're just going to say anything, if we're talking pointing inwards, radially inwards, like along the radius, that is going to be positive. And if we're talking there's a force that is radially outwards from the center, that is going to be a negative force. We're just going to add up those forces, and we'll see that is the net force. We're going to call that centripetal force. Okay, so just making sure that we understand centripetal force is not its own force. It is one or more of these other forces. Here are some examples: tension, friction, gravitational, normal, etc. So that means the net force never being on the free body diagram. That also means the centripetal force would never be on the free body diagram. Now we're going to talk about different types of forces that we might be using. This picture, by the way, is someone doing a hammer throw. So you can see there's going to be a lot of tension in there because we've got a rope. Let's see some other forces. All right, so we're moving out. We got this turntable here, and I had to wait till the end of the month so I could have I could cash my paycheck. Here it is, right here. I've got 6 pennies, and what we got is these pennies on this turntable, and we're going to start spinning the turntable. And why are the pennies staying in place? Well, right now that's because there is adequate friction between the pennies and the turntable. Now, this is a cool application of what we might be thinking about when we're driving. If there's not enough friction, if we're going too fast, what do we notice? The pennies are going outwards. Okay, now this penny out here, or in the center, had the smallest amount had the smallest tangential velocity because it had the smallest radius. If we saw these moving, it seemed these were going the fastest, so that they were spinning outwards earliest, right? Let's go ahead and move on to another one. Oh, and as this was turning around, what did you notice here? This is kind of a simulation of having guardrails, right? So we had, oh, maybe even, this was going around, and if the car doesn't stay on the road, if the car doesn't stay on the road because of friction, what do they often have along the sides of the roads? That would be a guardrail, and that is going to help keep the car in. That would be a normal force pushing inwards, pushing the pennies inwards. So friction was originally the thing pushing inwards on the pennies, and then we had this normal force. Let's see if we can do another force too. Okay, now here we have one of these constant velocity buggies doing not so constant velocity anymore. Notice it is going around in this circle. How do I know it's going around in a circle? Well, because it's a circular path, right? Okay, and it's got, as you can see, there's this string right here. It's going around in a nice constant radius. Now, if this string, this is a tension force, if this tension force were no longer there, what would happen? Let's see if I can get it like this. Into the box. Stop. Okay. Nope, caught up in there. Goes into the box. Now, we're going to talk about that in just a second. Okay, so we saw some cool examples of tension. That was that last part with the string. Friction and normal force causing circular motion. And in the next subunit, we're going to be talking about gravitational force. But we'll have to hold off on that. Let's talk about this centripetal force. We know that centripetal means seeking the center. Century means center, and petal means going towards or headed toward it, or seeking, as it says. So we had a string going around, or a string tied to the buggy going around like that. Now we have a string tied to a ball, and this is, I guess, supposed to be me. I don't know. The ball is being swung around like this. Why does it go in the circular path? Well, the idea is this force, in this case tension, is causing the circular motion. Now, the velocity of this ball is going to be perpendicular to the radius. Okay, so we have this tangential velocity right up here, and then the centripetal force, which is the cause of the centripetal force here is the tension that is going inwards. So centripetal force, which, as we said, is tension force. And the acceleration is also going to be inwards, a sub c. You say, okay, that's why the ball is going around, and it'll keep going around, and the ball is not going to be speeding up or slowing down because the force, and therefore the acceleration, they are perpendicular to the velocity. If the velocity and acceleration were in the same direction, they'd speed up. If they're in opposite directions, they'd slow down. Because they're perpendicular, wait a minute, no work is being done. Oh my goodness. Circling back. Ah! Now what happens if the string were to break? Which way would the ball go? Like inwards, and then, or would it kind of continue go around? Would it go up? Okay. So which direction does the ball go and why? Hopefully you can have deduced this from the demonstration that we just saw, as well as the different videos. It's going to go along path C. And the reason it would go along path C is because once this centripetal force, in this case the tension, is gone, there's no reason for the ball to continue going around. It's just going to continue on in the path that it was most recently traveling. That's Newton's first law. Objects in motion stay in motion unless there's this net outside force. As soon as that net outside force is gone, we're just continuing in a nice constant velocity. Okay, so let's make sure that we understand centripetal versus tangential. So the ball was wanting to go in a straight line, just like the buggy was wanting to go in a straight line, but the string kept pulling it back. In this case, it was tension, but as we said, there could also be frictional force, also be gravitational force, and normal force. Okay, so the string is pulling, the string is exerting an outside force. Okay, and that force is causing circular motion. That is the centripetal force. Remember, centripetal just means the net force. So here we have, this is the velocity, and then this is, which is tangential, making sure that we understand tangential. And then this guy here is the force as well as acceleration. Force and accel. Okay. And this is centripetal. Okay. So make sure that you understand the difference between the centripetal and the tangential. Tangential is for the velocity. Force and acceleration are the ones heading toward the center. That is the centripetal. Okay, so the velocity of the ball is always tangential, but the force and acceleration are always toward the center, perpendicular to that direction of motion.